Welcome to the deep dive. We're tackling a really fundamental concept today, something that comes up a lot when you're talking about building robust and scalable applications, multi-leader database replication.
Yeah, absolutely.
And, if you're aiming for senior level roles, especially in software engineering, understanding distributed systems and how we handle data across multiple nodes is, well, it's absolutely key.
Definitely. It's a common interview topic for a reason.
So our goal in this deep dive is to get a clear picture of what multi-leader replication is, why it's a strategy you might consider, what the real advantages are, and perhaps most importantly, what the potential pitfalls and complexities look like, especially when we're dealing with systems spread across multiple data centers.
Exactly. We're diving into the idea of having multiple points where you can write data to your database. And I think to really appreciate why this is a significant architectural choice, it's helpful to first consider the more traditional setup, the one where you have a single source of truth for writes.
Okay, let's unpack that then. With single leader replication, you've basically got one main database server, the leader, and all the write operations, they have to go through it, right?
Right.
These changes are then copied over to other database servers, the followers, which usually handle read requests. What's the core limitation we run into with this kind of setup?
Well, the fundamental constraint is that if you lose connectivity to that single leader, for whatever reason, maybe a network issue between you and the server, maybe the server itself has a problem, you're simply unable to perform write operations on the database.
Okay, so writes just stop.
Exactly.
Yeah.
This can effectively halt the write functionality of your entire application. It's also worth noting that even in systems where you partition your data into separate, independent segments, each of those partitions typically still relies on a single leader to manage writes for that specific data segment.
Right, so it's still a single point of entry for writes, just maybe at a more granular level within the overall architecture. Okay, so if we're looking to overcome this bottleneck, that's where multi-leader replication comes into play, is that right? What's the basic idea?
Precisely. Multi-leader replication, like the name suggests, allows more than one database node to accept write operations. So instead of just one leader, you have multiple. Now, here's a really crucial aspect.
Yeah.
Each of these leaders also functions as a follower to all the other leaders.
Okay, so they're all talking to each other.
Yes. So when a write occurs on one leader, that change is then propagated, forwarded to all the other database nodes that are also acting as leaders. You might also hear this approach called master-master replication or active-active replication.
Master-master, active-active. Okay, those terms definitely paint a picture of multiple nodes handling writes. Now, given that it seems to add this extra layer of complexity, when would you specifically choose to implement multi-leader replication? It doesn't sound like it'd be the default choice for, say, a simple web app.
You've hit on a key point there. Generally, deploying multi-leader replication within just a single data center probably isn't advisable.
Why is that?
Well, the increased overhead of managing it, the complexity, often outweighs any potential advantages you might gain in that kind of localized environment. But there are specific use cases where it becomes a really valuable and sometimes even necessary architectural pattern.
Okay, let's dive into those then. Where does multi-leader really prove its worth?
Okay, so one of the primary scenarios is in operating across multiple data centers. Imagine your application's database is distributed across several geographically diverse locations.
Right, like maybe one in the US, one in Europe, one in Asia.
Exactly. Perhaps to enhance fault tolerance in case an entire data center, has an outage, or maybe to position data closer to users in different regions to minimize latency for them.
That makes a lot of sense from a resilience and performance perspective. So how does multi-leader compare to the single leader model in this kind of multi-data center deployment? What's the difference?
Well, think about it. With a single leader in a multi-data center setup, all write operations, no matter where the user is, have to travel over the internet to the specific data center hosting the leader.
Okay, so even if I'm in Europe, my write has to go to the US leader first.
Potentially, yeah.
Yeah.
And that can introduce substantial delays, effectively undermining the performance benefits you were hoping to get by having read replicas closer to some users. Plus, it creates a really significant dependency on the network connectivity to that one leader's data center. Multi-leader in this context, it prioritizes local write latency and availability over super strong immediate consistency across all sites.
Right, that inter-data center latency could really degrade the user experience, waiting for a write to hop across the Atlantic and back.
Yeah. So how does adopting a multi-leader approach fix this?
Okay, so with multi-leader replication in a multi-data center architecture, you can designate a leader in each data center. So if a user in Europe makes a change, that write can be processed by the local leader within the European data center much faster.
Okay, so it happens locally first. Exactly. Then that change is replicated asynchronously, meaning not immediately holding up the user to the leaders in the other data centers, say in North America and Asia. This significantly reduces the perceived latency for the user because the write doesn't have to travel across continents before being acknowledged. That inter-data center network delay is essentially masked from the user's perspective.
Okay, that's a pretty compelling benefit for performance. What about when things go really wrong, like an entire data center goes offline? How does multi-leader handle that compared to single leader?
Right, good question. In a single leader system, if the data center containing the leader goes down, you're in a failover situation. You have to initiate a procedure, promote one of the followers in another data center to become the new leader. This process can take time, and depending on how it's set up, potentially involve some data loss from recent writes.
Yeah, failovers can be tricky.
They can be. Now, with multi-leader, each data center can continue to operate more or less independently, even if one of the others goes offline. Writes can still happen locally in the remaining data centers. Then, when the failed data center recovers and comes back online, the replication mechanisms will kick in and synchronize it with all the changes that occurred while it was down.
So it sounds like it offers a higher degree of resilience, maybe, at least in the face of complete data center outages. What about more common network hiccups between data centers? Just temporary glitches?
Again, multi-leader tends to be more tolerant of those issues. Remember, communication between data centers often relies on the public internet, which, let's face it, can be less stable than your nice, controlled local network.
True.
A single leader system is quite sensitive to problems with this inter-data center link, especially if writes are configured to be synchronous across it, waiting for confirmation. If that link fails or gets really slow, write operations can just get blocked.
Which brings us back to writes stopping.
Exactly. Multi-leader, typically using asynchronous replication between data centers, can generally withstand these temporary network interruptions much better. Writes can continue to be processed locally in each data center, and the replication just catches up once the network connectivity is restored. Now, this asynchronous nature, it's important to remember. It means that writes aren't guaranteed to be instantly reflected on all leaders simultaneously. You can have temporary differences in data across the nodes. That's the trade-off.
Okay, that asynchronous part is key then. It provides tolerance but introduces potential temporary inconsistency. That sounds pretty robust for multi-data center scenarios, though. Are there specific database technologies that have this multi-leader capability built right in, or is it usually an add-on?
Both, actually. Some database systems do offer native support for multi-leader configurations, but it's also quite common to see it implemented using external tools that kind of sit alongside the database and manage the replication.
Like what kind of tools?
Well, for example, you might encounter Tungsten Replicator, used with MySQL, to manage these asynchronous replication streams. Or BDR, which stands for bidirectional replication, with PostgreSQL. Golden Gate is a well-known one, often used with Oracle, especially for replicating between different types of databases.
Interesting. So you have options depending on your stack. Okay, so multi-data center is one key area where multi-leader shines. What's another significant use case where this comes up?
Another really important scenario is when you have clients, like apps, that need to function even when they're offline. Think about calendar applications we all use on our various devices, phones, laptops, tablets.
Right, yeah. You expect to be able to add an event even if you're on a plane with no Wi-Fi.
Exactly. You expect to be able to view your schedule and add new events even if you don't have an active internet connection right then.
Okay, so how does multi-leader fit in there?
Well, in this situation, each of your devices essentially has its own local database that acts as a leader. It can accept write requests, like when you schedule that new appointment on the plane, even when you're offline.
Ah, so my phone's calendar app has its own little database acting as a leader.
Precisely. Then, when your device regains internet access, there's an asynchronous multi-leader replication process, basically a synchronization or sync that takes place between all the replicas of your calendar data. So between your phone, your laptop, maybe a central server somewhere, the delay in this replication can vary a lot, maybe minutes, maybe hours, maybe longer, depending on when you get back online.
So each device is almost acting like its own tiny data center with a highly unreliable network connection to the others.
That's a great way to put it.
Yeah.
Exactly. And, well, as anyone who has experienced frustrating issues with calendar synchronization can probably attest, implementing this type of multi-leader replication reliably is incredibly challenging.
Oh, yeah. I've definitely had appointments disappear or duplicate.
Right. The history of problematic calendar syncing solutions really underscores the inherent complexity involved. It's not easy. Some database systems, actually like CouchDB, were specifically designed with this kind of occasionally connected multi-leader environment in mind, trying to simplify managing it.
That's a really clear analogy with the calendar apps. It perfectly illustrates how multi-leader can be used in these distributed, sometimes offline settings. Is there maybe another key application for this approach?
Yes, another interesting application is in the realm of collaborative editing. Think about real-time collaborative document editing platforms like Google Docs or similar tools where multiple people can simultaneously work on the same document.
Okay, yeah, I can see the parallel there. Multiple users are making changes, kind of like multiple leaders performing right operations.
Exactly. While we might not immediately think of it as traditional database replication, it shares many of the same fundamental principles. When one person edits a document, their changes are instantly reflected in their local view, right?
Yep, you see what you type immediately.
And then those changes are asynchronously replicated to the server and to all the other users who are concurrently editing that same document.
That makes sense. The goal is to get those local changes out to everyone else as quickly as possible so it feels like real-time collaboration.
Right. Now, if your main goal in this scenario was absolute guaranteed consistency with zero possibility of conflicting edits, you could use a locking mechanism.
How would that work?
Well, it'd be more like single-leader replication with transactions. Only one person at a time could get a lock on the document or maybe a section of it, make their changes, and then release the lock. Everyone else would have to wait their turn.
That sounds like it would really slow things down, though, wouldn't it? Like having to queue up just to type a sentence in a shared document.
Exactly.
Yeah.
It would totally hinder the real-time collaborative feel.
Hmm.
So for a smoother, more responsive real-time experience, you often want to work with really small, granular units of change, maybe even individual keystrokes, and avoid locking. But doing that, allowing multiple users to edit concurrently without strict locking, immediately introduces all the challenges associated with multi-leader replication. Because now you have multiple independent sources making potentially simultaneous modifications to the same thing.
So it's that classic trade-off again. You trade strict consistency, which you get with locking, for the fluid real-time feel of multi-user editing, but then you have to deal with the potential conflicts that come from, essentially, multi-leader replication.
Precisely.
This all sounds great in terms of the benefits, performance, offline, collaboration, but you mentioned earlier there's a significant downside, conflict management. Can you elaborate on that a bit more? That sounds like the scary part.
It is, yeah. This is really the major challenge with multi-leader replication. Because you have multiple nodes that can accept writes independently, it's entirely possible, even likely, for the same piece of data to be modified concurrently on two or more different leaders.
Okay, like two people editing the same sentence in that doc at the exact same time, or maybe updating the same customer record from different data centers.
Exactly those kinds of scenarios. When these conflicting changes are subsequently replicated to the other leaders, the database system needs a mechanism, a defined way, to determine which change should win, or maybe how to merge the changes, or how to reconcile these divergent updates. This need for robust conflict resolution is just fundamental to multi-leader replication. The core trade-off here is sacrificing that strong, immediate consistency you get with single leader for higher availability and lower write latency in these distributed scenarios.
That sounds like it could get very complicated very fast. How do these systems actually manage these conflicting write operations? Is there a standard way?
Well, there isn't really one single standard way.
Mm-hmm.
There are various strategies for conflict resolution, and it's a pretty significant area of research and engineering in its own right. You might have strategies like last write wins, based on timestamps, or maybe merging rules for certain data types, or even flagging conflicts for manual resolution. The crucial point to understand, though, is that you must have a defined strategy in place.
We can't just ignore it.
You absolutely cannot just ignore it and hope it sorts itself out. Effectively handling these write conflicts is a critical, non-negotiable aspect of designing and operating any system that uses multi-leader replication.
Okay, so conflict resolution is a major hurdle, a necessary complexity. Are there any other potential difficulties or considerations that come with implementing multi-leader replication, other things to watch out for.
Absolutely. Just the overall increased complexity compared to single-leader architectures is a big factor. Setting up, managing, monitoring a multi-leader environment, it's just inherently more challenging. And because multi-leader functionality is often, though not always, kind of bolted onto existing database systems, rather than being a core design principle from day one, you can run into subtle configuration issues and sometimes really surprising interactions with other database features.
Surprising interactions. Could you give some specific examples of those potentially problematic interactions? What kind of features might cause trouble?
Sure. Things like auto-incrementing keys, where the database automatically generates the next sequential ID number. That can become problematic really quickly. If you have two independent leaders both generating new IDs, you could easily end up with duplicate primary keys when the changes replicate. Big problem.
Yeah, that sounds bad.
Triggers, too. Those are pieces of code that automatically run when certain database events happen, like inserting or updating data. They can also behave unpredictably in a multi-leader setup. Maybe they fire multiple times when a change replicates, or they fire in an inconsistent order across different leaders, leading to weird side effects.
Okay, so triggers can get messy.
Definitely. And similarly, integrity constraints, rules that enforce data validity, like ensuring a foreign key exists, might get violated if conflicts aren't resolved correctly before the constraints are checked, leading to inconsistent data states across the cluster. Because of all these things, multi-leader replication is sometimes seen as dangerous territory.
Dangerous territory.
Yeah, it's often something to avoid if you possibly can, unless the specific requirements of your use case genuinely justify taking on that added complexity and the potential for these kinds of unexpected behaviors and configuration pitfalls.
Wow. Okay, so while it offers some really attractive benefits, it definitely sounds like you need to approach it with your eyes wide open, with a deep understanding of the potential downsides, and importantly, with well-defined strategies in place to manage those challenges, especially conflict resolution. So just to quickly summarize our discussion then, we started by looking at the limitations of single-leader replication, particularly in distributed environments like multiple data centers. Then we explored multi-leader replication, where multiple nodes can accept writes, and those changes are shared amongst them. We looked at key use cases, improving performance and availability across multiple data centers, enabling offline client operations like those calendar apps, and even supporting real-time collaborative editing. And it's big, but we also highlighted the significant challenge of managing write conflicts, which is inherent to the model, and the overall increase in system complexity, plus those potential tricky interactions with existing database features like auto-increment keys and triggers.
That's a really concise and accurate summary. I think the key takeaway is that while multi-leader replication can be a powerful tool for certain specific scenarios, especially those involving distributed systems or the need for offline capabilities, it introduces significant trade-offs. And the big ones are around maintaining strong data consistency and managing the operational complexity that comes with it.
Right. So thinking about someone preparing for a technical interview, maybe for a senior software engineer role, and they're discussing different database architectures, where would these trade-offs of multi-leader replication likely be a critical discussion point? What are some key questions they should be prepared to ask or maybe answer about a system that employs this pattern? It seems like a deeper understanding of not just what it is, but when and why you'd choose it, and perhaps even more importantly, when you should maybe avoid it, is really crucial here.
Absolutely crucial.
And they should probably be ready to talk specifics about conflict resolution strategies and the implications for data consistency, right?
Absolutely. Thinking in terms of those real-world architectural decisions is essential, like asking, when would the benefits of local rights and high availability in a multi-data center setup truly outweigh the complexities of potential data conflicts? Or, in an offline-first application, how robust and, importantly, how user-friendly is the conflict resolution mechanism? Because users hate dealing with conflict.
Yeah, nobody wants to sync conflict-detected error.
It's exactly. Or for collaborative editing platforms, what level of eventual consistency is actually acceptable versus the need for that real-time responsiveness? These are the kinds of insightful questions that really demonstrate a strong understanding of the architectural trade-offs involved. And furthermore, being able to clearly articulate the potential challenges with things like auto-incrementing keys or triggers in a multi-leader environment that showcases a practical, hands-on grasp of the operational realities. It shows you're not just thinking theoretically,